Hey everyone, I'm sorry I didn't get to finish this problem in the 10 a.m. section today. So I told everyone that I would make a video about it. So I'm just going to go through this last practice problem on the handout from today. So in this is a problem about how risk-weighted expected utility maximizers will sometimes fail to obey Good's theorem. So remember, Good's theorem is about how there is always value in doing an experiment that will give you some information about your decision. So in fact, for risk-weighted expected utility maximizers, it's sometimes going to be rational to pay to avoid getting information that we would get from such experiments. This question is going to show why that's the case. So here's the question. Suppose that you are a pirate with $100 on your ship. One day you are standing by your dock and you notice that a small raft carrying $900 is sinking. If you attempt to sail to the raft and your ship is seaworthy, then you can recover the $900 and of course keep the $100 that's on your ship. If you attempt to sail to the raft and your ship is not seaworthy, then you will lose your $100 in addition to the $900 on the raft. So you'll lose everything and end up with no money. If you don't attempt to sail to the raft, your $100 will be safe, but you will not get the $900. You have an opportunity to test your ship's seaworthiness before deciding to sail out to the sinking ship, sail out to the sinking raft. If you are a risk-weighted expected utility maximizing pirate with a risk function of R of P equals P cubed and a linear utility function for money, should you perform the test? So I just want to start out by explaining what's going on in this table. So here we have two actions, either attempt to go out to the raft or not to go out to the raft. So, and here we have, various combinations of X and E. So X represents the fact that the ship is in fact seaworthy, whereas not X would mean that the ship is not in fact seaworthy. E is the result of the experiment. So E means that the experiment tells us that the ship is seaworthy, whereas not E means that the experiment tells us that the ship is not seaworthy. So here, the probabilities that we're given tell us a little bit about the experiment that we're doing. So in particular, these probabilities tell us that the test is pretty reliable, but not completely reliable. In particular, there's a 2% chance that the test will give us a false negative. So a 2% chance that the test will tell us that the ship is not seaworthy, when in fact it is seaworthy. And there's a 1% chance that the test will give us a false positive. So a 1% chance that the test will tell us that the ship is seaworthy when in fact it's not seaworthy. Okay. And it's going to turn out that this incomplete reliability of the test is what makes risk weighted expected utility maximizers fail to obey Good's theorem in cases like this. Okay, so we're asked whether we should perform the test, right? So whether performing the test has a greater expected utility than not performing the test. So this question starts out much like other questions where we would calculate the value of doing an experiment. First, we want to find the expected utility of not doing the experiment. Then we're going to calculate the expected utility of doing the experiment. And then we're going to compare them. And if the value of doing the experiment is greater than the value of not doing the experiment, then we should pay to do the experiment. And if it's less than the value of not doing the experiment, then we should pay to not do the experiment. So let's start out by first calculating the value of not doing the experiment. So here we're just going to take the risk-weighted expected utility of A, and we're going to take the risk-weighted expected utility of not A, and whichever one is greater is going to be the risk-weighted expected utility of not performing the experiment. Okay, so here we have for the risk-weighted expected utility of A, So we're looking at this first row of the table. Notice how there are two possible outcomes here. There's $1,000 and there's $0. Those are the two possible outcomes. So we know we're going to use the two outcome equation for risk-weighted expected utility, which is REU equals R of P times U max plus 1 minus R of P times U min. So we're just going to plug our values into that. Okay, so R of P, which is the probability of the max, is 0.89 plus 0.02. So we're going to have 0.91 cubed times U max, which is 1,000, plus 1 minus R of P, which is 0.91 cubed times U min, which is 0. And that gives us, according to calculations I did earlier, 753.571. So that's the risk-weighted expected utility of A. Now, the risk-weighted expected utility of not A is really easy because if we look at the not A column, we get $100 no matter what. So the risk-weighted expected utility of not A is going to be 100. 100 is less than 753.571. So it's going to turn out that the risk-weighted expected utility of A is the risk-weighted expected utility of not doing the experiment. So if we don't do the experiment, we would choose A, and we would get the risk-weighted expected utility of 753.571. Okay, so that's the first part of the problem. Now, the second part of the problem is to find the risk-weighted expected utility of doing the experiment. So there are two things we want to calculate. We want to calculate the risk-weighted expected utility of doing A, given that we learn from the experiment that the ship is seaworthy. And we also want to find the risk-weighted expected utility of doing A, given that the experiment tells us that the ship is not seaworthy. And we don't have to calculate the risk-weighted expected utility of not A because we know that's just going to be 100, because for not A, no matter what, we get $100. Okay, so let's start by calculating the risk-weighted expected utility of A given E. So what this means is we're going to look at we're just going to focus on A, the row with A, and we're only going to focus on the columns where E occurs. So these two columns, right? We're conditioning just on cases where E occurs. So notice that this gives us a case where there's a max, only two possible outcomes, a max and a min. So we're going to use, again, that two outcome formula for calculating risk-weighted expected utility. So we're going to have to take the conditional probabilities. So the probability of max is 0.89 over 0.9, right? Because we have to do 0.89 plus 0.01 cubed, because we have to take the risk-weighted expected utility, times U max, which is 1,000, plus the 1 minus the risk-weighted expected utility, the risk-weighted probability of max times the min. This should be 1,000, not 10,000. Sorry about that, times 0. Okay, and that's going to turn out to be, according to my calculations, 967.04. So 967.04 is greater than 100. That means that if we learn E, so suppose we do the experiment and the experiment tells us that the ship is seaworthy, we would choose A because the expected utility of doing A, 967.04, is greater than the expected utility of doing not A, which is just 100. So what this tells us is that if we do the experiment and the experiment tells us that the ship is seaworthy, then we would choose A. So now let's see what we would choose if the experiment told us not E. So we're going to go back to our table And again, we're just looking at the first row. And now we're going to condition on not E. So we're looking at these two columns of the table. Okay. So again, we have a case where we're calculating risk-weighted expected utility for two possible outcomes. So we're going to use the two outcome formula. So first we have the risk-weighted probability of the max, which is 0.02 over 0.1 cubed times U max, which is 1,000, plus 1 minus the risk-weighted probability of the max times U min, which is 0. And that turns out to be 15.62. Okay, so 15.62 is less than 100. So that means if we did the experiment and the experiment told us the ship was not seaworthy, then we would choose not A. And that's because the expected utility of not A, 100, is greater than the expected utility of A given not E, which is 15.62. Okay, so this yet doesn't give us a full picture of the expected value of the experiment, because depending on how the experiment goes, we're going to choose something different. So here's the way to figure out the expected value of the experiment. So first, I'm going to construct a table. So the table is going to have the same outcomes as before. And remember that we're trying to figure out whether to do the experiment or not to do the experiment. So let's compare those two outcomes. So we first have the option of not doing the test and just doing A, right? So remember from up here, we figured out that the REU of A is greater than the REU of not A. So if we don't do the experiment, we're going to choose A over not A. So if we don't do the test and we choose A, then we get the following payouts. And this is just copied from the table above. And then we have the probabilities. I think those are all right. Let me check. Yeah, okay. Oh, these two should be reversed. Okay, so one option is to not do the test and just do A. The second option is to do the test and do what the test recommends. Remember, what the test recommends depends on whether the test tells us that the ship is seaworthy or not seaworthy. So when the test tells us that the ship is seaworthy, remember that we chose to perform Act A, which gives us the greater expected utility than not A. So in cases of E, we're going to do A with the following outcomes. Okay. And if the test tells us not E, then remember we're going to do not A, because 100, the expected utility of not A is greater than 15.62, the expected utility of A, given not E. So remember that not A gives us $100 no matter what. So if we do the experiment and it tells us not E, then we're going to get $100. Okay, so we know the REU of the first course of action. That was something we calculated earlier, 753.571. And now we want to calculate the REU of doing the test and then doing whatever the test recommends. So this is just going to be another simple case of calculating REU. So this is a case where we have three possible outcomes. 1,000 is our max, 100 is our mid, and 0 is our min. And the three outcome formula is that like really long one. It's somewhere here. Yeah, it's like this one up here. So you should have it on hand. There was a small typo on the handout, which I'm sorry about. There shouldn't be a parentheses there. It should be another closed parentheses there. But okay. So we're going to calculate this. So the REU of doing the test is going to be 0.89 cubed times 1,000 plus 0.99 cubed minus 0.89 cubed times 100 plus 1 minus 0.99 cubed times 0. And that turns out to be 635.44. Okay, so the 635.44 is less than 753.571. And this is something that never happens with expected utility. So it's never the case that doing a test, that the expected value of doing a test is less than the expected value of not doing the test. But because of risk-weighted expected utility, this is a conclusion that occurs. So we conclude that REU of test is less than REU of no test. And that means that you should actually be willing to pay to avoid doing the test that gives you information about whether or not your ship is seaworthy. So a couple of things we're thinking about, which I indicate in the discussion questions, are, is this information, is information that is misleading the same as information that's not veridical? So, one question being, does the fact that false negatives and false positives are possible affect the way that the question is phrased? And finally, we should think about Bouchak's, whether this conclusion fits with Bouchak's account of risk avoidance. So whether this makes sense given the attitudes and behaviors that are characteristic of risk avoidant agents. That might not be characteristic for other kinds of agents. So if you're risk avoidant, it might be the case that you're willing to pay to avoid risk in a way that Laura Bouchak finds acceptable. Okay, let me know if you have any questions about this problem, and good luck on the problem set.